to thank. I want to take this opportunity just to thank everybody and to participate in this seminar series, and also other members of this organized committee to keep this thing going. And then I wish everybody a happy holiday. And then we're looking forward some new seminars for the next year. Okay, I think I will give back to Jennifer. You can probably start the seminar now.
Very good. Thank you, Xinyan. So we are very pleased to welcome Jifeng Hu to give us a seminar today on the most recent BESIII results. Jifeng is a senior scientist at South China Normal University, and he's been a senior scientist there since 2020. So Jifeng, thank you for being here, and whenever you're ready, please begin.
Okay, so I can start now?
Yes, yes.
Okay, thanks. And today I'm quite glad to accept the invitation from Dr. Jennifer. And I'd like to take this opportunity to thank Dr. Jennifer for her very kind invitation, since I'm also very glad to share a recent work published by the BESIII collaboration. And thanks, Professor Xinyan, and I know him for quite a long time when I was a graduate student. And I'm very, very happy to see him again today. And this published work is entitled with Oscillating Features in the Electromagnetic Structure of the Neutron. It's my pleasure to address this seminar on behalf of the BESIII collaboration. Thus, in this talk, I will talk about this work from the viewpoint of the BESIII collaboration. Okay, let's start. And today we have a very deep insight into our universe. We know that the dark matter and also dark energy, and even we have not found any evidence or something direct evidence to prove that dark matter and dark energy. And also we know that the nucleons consist of major component of the visible matter. And besides the continuous effort made to understand dark matter and dark energy, actually nucleons have not completely understood yet. They are typical bond state of interaction and just lies in the non-perturbative region. Thus, the internal structure cannot be well calculated from first principles of theory. But we can measure it. This is very good to us. In particular, we studied quantum properties. For example, its life, its spin, and its mass, and its coupling, and so on. And here I copy some pictures from some art in local, Guangzhou, to represent its spin. For example, it's a very nice picture. And we just with this kind of windows to insight into its internal structure to understand, and the very complicated structure inside of the nucleus. So let me begin with a very quick and short review, and then switch to the topic to be discussed today. And we know that discovery of radioactivity opened a door to the microscopic world. And Rutherford and his student, Chadwick, discovered the proton and the neutron respectively, and leaving a famous story in scientific history. And just to look at this picture, is a very old photo illustrating the equipment in the Rutherford laboratory, and where Chadwick carried out his research. To make it clear, let's see a demo. On the experiment setup. We can see that actually this setup includes three components, very key component, a particle source here, and also a target, and followed with a detector. Okay, and even today, they are still the core component. Of course, today we can make very new particle source and a new target and new detector with the very most advanced technique. And Chadwick published his research in 1932, and in his paper, he named the radiation of with great penetrating power as the neutron. This is, as we know from the history. And so the existence of the nucleon was well established. And I just copy a photo from the Nature website. And here is just, I mean, you can see this paper is only occupy half of the page, very short and concise. And then we know that actually the Second World War began, and almost 10 years or more interrupted. So there is no very big scientific research. Of course, we have to mention that the Professor Otto Stern measures the normally magnetic moment, and that is a hint that the proton is not a Dirac particle. We know that. So, and actually after that, I mean after Second World War, and in 1950s, and the American physicist Hofstadter did the electron-proton scattering experiment and discovered the structure of the proton. And this unprecedented success actually adopted a new technique, the particle accelerator, in charge of increasing the energy of charged electrons to several hundred million electron volts. And this energy is much, much higher than the energy of the beta rays. So as illustrated in the red plot, we can see that the curve made by the experiment cannot be explained by any kind of the theoretical predictions. So I copied this picture from the website because it is found from the search engine. And experiment result cannot be explained with, for example, the calculation with a point on the hypothesis of a point-like particle scattered by another point-like particle. And more important, this experiment give a breakthrough to the traditional concept that how to define the elementality. So in his speech of the Nobel Prize, the Hofstadter said, and this is a long, sentence, and just read the last one. So that the elegant idea of elementality must be abandoned. So this is a very big breakthrough to the traditional concept. And now let's just see another very important concept that proposed for the first time in his experiment. It's just the form factor. To make it clear, and let's just compare two simple cases. The first one is a point particle scattered by another point-like particle. And the second is a point particle, a structured particle scattered by a point particle. So let's just compare the different cross-section. We can see that in the red side, labeled with the red rectangle, and we can see this atom is in charge of the structure of the structured particle. That means this atom is only dependent on the squared momentum transfer and also depending on the scattering angle. But if we integrate in the scattering angle, then we get a term that only dependent on the Q square. Okay, so to really describe the structure of the nucleon, okay, let's just make some normalization with mode cross-section. And then we get a dimensionless observe. This observe is just, a parameterized function depending only on the momentum transfer Q square. And also we can think from another side to see this function. That is, imagine the nucleon structure using the electromagnetic probe. Okay, this is how we see or we treated the structure of nucleon from experiment side. And also, if we understand the form factor in theory, that it is just a hadronic current. That is coupling from, two different components. One is the Dirac form factor, is named F1, and another one is the polyform factor. It's just in charge of the magnetic interaction. So let's now combine the F1 and F2 gives the Sachs formula. Here, the Sachs proposed two new, definition of form factor. It's the electric form factor and the magnetic form factor. This is widely used in experiment, and today we will see that. And we also made the effective form factor, and later we will talk about again. Okay. And we know that a lot of facilities followed. And here I did not list all of them. And among them, the electron-positron collider at Beijing was built in 1988. So I will discuss more about this collider later. Now let's just put it aside. Here, I just see that there's a lot of facilities and many experiment and gives very, very precise measurement again. And anyhow, if we see all of these experiments, they can be divided into two types. One is the scattering experiment. This picture is quite simple. We just use the electron as our projectile and to detect the structure of the target. Okay, and this kind of experiment had a key feature, that's the energy, the beam energy of the electron. So anyhow, the key is to accelerate the high energy projectile as possible as the facility can. And another one is annihilation experiment. And the key is to achieve high luminosity as possible as the facility can. And how, if we compare two kinds of experiments, we can see that the Q square is also differs. And in the left side, for the scattering experiment, the sign is negative. And in the right side, the sign is positive. So this is quite a different features. And we name that in the left side is the space-like region, and the right side is the time-like region. This is the standard definition. And whatever in the space-like region or the time-like region, they also, describe the structure of the nuclear. But we just to understand the nuclear from the view from the side of the friends. This is a very good description that I just copied from Professor Austin's talk. And here we can see that in the space-like region and also in the time-like region. And here we have an unphysical region. That means because in this region, the nucleon and antinucleon pairs cannot be created because here as energy is lower than the energy threshold production. So that means this is just the fence. Okay. And the interesting thing is both regions are connected. If we make some assumption, for example, if we think that the form factors in the Smith-like region is analytical and also continuous function, it should be connected with the complex ones in the time-like region. That means they form a closed loop in the complex time. So both form factors in the space-like region and in the time-like region are bridged with the dispersion relation. That means if we see the imagined part of form factor in the time-like region, it could be changed to the form factor in the space-like region here. And that way to give a very interesting prediction that in the infinity, there should be give equal and modular for the form factors. These are natural conclusion from mathematics, nothing about to physics. Okay. And of course, here we know that we can't test this equation because we never can get so higher energy for infinite energy. Okay. So we know that many experiments measured and carried out, and make continuous effort to measure the neutrons form factor, not neutrons, protons form factor. I'm sorry. And we know that we get more and more precise results. And however, one particle is effective. It's just the neutron. And in the past a long time, we have no data. And if we if we only put aside to understand the annihilation experiment, we can see that in 1998, the FINICE experiment published the first measurement about the electron-positron annihilation to neutron and antineutron. So, and followed with by the SINT experiment in 2014. And here, the both experiments give a conclusion that we can see that with their result, the photon coupling to the neutron is a little stronger than the photon coupling to the proton. And here, we just put the Barbara's result as our reference. And in last page, I'm sorry that I want to, I didn't mention that in my talk, I will only focus on the annihilation experiment. Okay. I'm sorry. So from the result of the FINICE and SND experiment, they just give concluding that a strong coupling, that the photon to the neutron is stronger than the photon coupling to the proton. So this is really a puzzle. I mean, this puzzle lasts almost over 20 years because from the simple quark model prediction that we know that it should be, we should be observe a more stronger coupling between photon to proton. So anyhow, this is puzzle is quite, confused. So we need to understand what happened. So this is the main topic of today. And we know that actually it's not so easy to address answer about, which coupling should be stronger because in theory, it's not so easy to make such a kind of calculation. Let's just see the predictions before the FINICE experiment. And we can see that, so we have so many models and they can make different conclusions. And the reason probably, and in one word, is nothing is impossible. The reason is quite simple because first, it's very difficult to construct a very, powerful model to see, to build a reasonable picture to make such kind of prediction. And another difficult, I think, is because we know that at that time, to make such kind of calculation, we need some fundamental parameters. And generally speaking, these parameters should be determined by the experiment. So at that time, we didn't know the values as precise as we know today. So if we make such kind of calculation, we will have a very large uncertainty. And how we can see that it's really difficult for theory to answer this puzzle, but we can answer this puzzle in experiment. Now the time goes into a new century. In 21st century, we have new technique, we have new detector, and like BESIII or Beijing electron-positron collider. So our question is, does the BESIII address something new about this kind of question? And here, let me just spend several minutes to introduce our collider and our experiment again. And here, I just show that, okay, this is our linear accelerator. They are in charge of accelerating the electrons, and they inject the electron positron beams and electron beams in a double ring storage. So, and then we manipulate their, the electrons and positrons, mix them and collider in the BESIII detector. And this is our detection hall. Okay, and of course, this is our very high luminosity collider. And the energy region just lies in from 2 GeV to giga electron volt to 4.9 almost up to the upgrade. So if we see the production after electron positron annihilation, we can see that are very, nice picture from here. And in the very low region, it should be rho omega phi state. And then we can detect the charmonium state. And also at the barrel, it should be bottomium state. And if we increase the energy, and we should see the Z. So, and here we can clearly see that how the BESIII and how the BESIII collider, works in the, which energy region. And also the BESIII experiment operates in the BESIII collider. And our detector is also a preceding frontier experiment. And also it's still under running in the Tau region. Also I will say that this is a unique equipment in this in search for the Tau physics. Okay, of course we have a very good detector design index, and see here you can see that whatever for the photons or charged particles, our detector could measure it in very precisely. In precision around 2% or less 2%. And of course, the BESIII collaboration is in charge of, managing or running the BESIII detector. And of course, our collaboration is an international research community working in the Tau physics. One important thing I will say here, to get a membership, even no fee is charged. This is, I think, special for international, research community. Okay. And my person, for me, I joined the BESIII collaboration at 2005. It's quite early time. And after now, I work in the South China Normal University. We joined the BESIII collaboration again in 2020. This is, for continuous scientific research, we have to get a membership in advance. Okay. Okay. Now let us talk about today's main topic: how to measure the form factor of the neutron. So at the annihilation experiment, we have two solutions: the beam energy scan and the initial state radiation return. For the first solution here, you can see that the electron and positrons are accelerated to almost the equal energy. Here they have the almost equal energy, but with opposite momentum. We then manipulate the beams for height clearance, change the beam energy, and repeat this procedure. So that's it to say we sample the form factors at a different energy or different squared momentum transfer. So this solution gives a very precise energy determination. Okay, this is special, or this is the future. And the second solution is called initial state radiation. And after the radiation photon takes away some energy, that means the center mass energy goes down to the region that we are interested in. So this is another solution. And compared to this, and we can see that the second solution is surprised in the production. That means by almost the alpha factor. So in this research, we will only focus on the energy sky solution, and we, with this solution, take quite a lot of data. This is, the methods used in this talk. Okay, so in the next, and I will only talk about the first solution here. So to perform the beam energy scan, we must choose reasonable, energy range, and determine the sampling time, the sampling energy, since we have a quite large range. But we need to determine which energy point is the best choice for us. Clearly, we have first to avoid the charmonium background. So that means our range of course, it restricts to from 2 GeV to 3.08 GeV. So this is our very important, option region. And with, of course, here, we have a lot of terminal state. We have to escape from this kind of background contamination. So in principle, below, 2 GeV is also an important region and also above the energy threshold here. So however, our machine is optimized near here, 3.77 GeV. That means if we perform our data taking around this energy region, we have sharply discounted luminosity. This is not good for data taking. So more or less, the 2 GeV is a balanced choice. So the lower energy region is set to here. Okay, this is our, very interesting energy region to carry out the whole form factor measurements. And finally, we collected almost 688 inverse picobar R scan data. And also, I have to mention that we use 10 billion GSI data for our detector calibration. This is also quite important for this measurement. Okay. Finally, I'm sorry. Okay, I'm sorry. Okay. Here you can see some Chinese characters. I didn't change them. Okay. We have sampling 18 energies. And here for each energy, and you can see here, we have the luminosity, integrated luminosity, also the the number of total events here. This is the number. And the whole data taking lasts almost 3 or 4 years, and from 2011 to 2015. And because if we want to perform the data taking, sometimes in the summer of the 1 year, we have to manage our detector and to maintain, and also to repair some potential problems. So this is will be the limited time. So for 1 year, we only have 7 months to make full run with our detector. So actually, the data taking lasts almost 4 years. It's a long time. So now the data is ready. Our question is how to extract the form factors of the neutron. So simply speaking, we have 3 steps. The first to hunt for 5 numbers here. These numbers are labeled with the rectangle. And we have to fix these 5 numbers very precisely. This is our main tasks. And the second one is theoretical assumption. And here we make assumptions like electron-positron annihilation with 1 photon. So with this assumption, we have some theoretical predictions. And of course, usually the GM and GE cannot be, simultaneously determined if we have no enough statistics. So that means to combine 2 form factors together, we can redefine a so-called effective form factor here. And we just combine 2 form factor together. So in this talk, I will demonstrate the effective form factor G measurement. And this is a special point, just to pay attention. And of course, the third step is quite easy, translation. And with our made cross-section and with the theoretical formula, we can make a quite easy translation. We can get the final result. Okay, so let's now to start from the 5 numbers. Okay, this is our core tasks. We can easily, or naturally think about the signal features, because this is reaction, 2-body reactions from 2 particles to 2 particles. So that could be easily understand for some kinematic features, the back to back angle or to crossing angle between one shower to another. So we can, hunt such kind of events, but it's not so easy because here, let's think about one thing. If we have a charged track, then along its trajectory, we can easily, associate the shower with this track. So this could be very easy. But if there is no charged track, that means we only see, some fired crystals and some fired, the time-of-flight scintillator. It's because very difficult to think about which signal should be combined or associated to the other signals. So this is our detector, set view. This is set view. This is, the view perpendicular to the beam direction. And from the inside to the outside is the main drift chamber. And the yellow line represents the time-of-flight scintillators. And around with the electromagnetic crystals here. And in the outermost is our muon detector. So let's now think about how to measure our signal events. Though we have to imagine that the signals in the EMC crystal, also in the time-of-flight scintillators, and we have to group these digit, electric from the electric readouts together, and to see which it should be the neutrons annihilation into our detector, or some probably from the anti-neutron annihilation in our detector. So combine all these signals, electric readouts, we can make some new reconstruction, and we call that is our event finder. So to get our signal event and from quite a lot of background event. Basically, we have three categories. That means we start from an event without any charged tracks, and then we know this is some purely neutral event. And then with this logic, we have category A, B, and C. They just denoted with the combination of the detector used. For example, category A, and actually with the electromagnetic calorimeter together with the time-of-flight detector, and together another one, a time-of-flight detector. And category B and C actually with the EMC and the plus MUC. So this kind of combination of three different solutions will compensate together. And also we design the whole event finder with three features. The first one is mutually exclusive categories. That means any event only be selected one of the three solutions. There is no event will be doubly counted. And of course, the second feature is we will maximize the signal use because this is quite clear. And of course, the third point is we perform a cross-check with three independent measurements. Okay, now let's just think about how to verify our selection logic, because this is some new event finder or new reconstruction packages. So we have to make this kind of proof to see how our selection logic work well. The first one, we think about the electron-positron annihilation to gamma. That means this process is quite similar to our signal process. And here we can see that we only needed to change a little bit some selections. That means, and keep the rest logic unchanged. That means we have to, we should get the result within our expectation. So clearly, we test the first shower, the second shower. That means the first photon and the second photon. Okay, and also the time of flight, because we know the speed of gamma, and we also know, its emerging direction quite easily. So we test the distributions, and all of the distributions are, I mean, within our expectation. And of course, if we perform more, for example, to compare the theoretical cross-section and the measured cross-section, and how they varies with the energy of the center, the electron-positron beams. We can see that almost, I mean, within our expectation. So that means our selection logic works well and just, I mean, successfully, I mean, to carry out a neutral process. And of course, we can use another process, BESIII, to neutron and anti-neutron to test our selection logic. And here is only the beam energy changed. And here BESIII is a little bit higher than our, I mean, data set. That is to say, after 3 solutions selection and with the full identical, I mean, analysis methods, we can measure the breaking fractions from of BESIII to neutron and anti-neutron, and we get a very comparable result from each other. So that means 3 solutions, I mean, also works well to do this kind of measurements. And now let's just count the other 4 numbers. The first 2 is the Monte Carlo efficiency, and also the radiation corrections here. For the Monte Carlo efficiency, we have so many, I mean, verifications. First one, we from the weighted method, also from the inclusive Monte Carlo sample after our selections. So that means follow all these selections, we can check the efficiency, how the efficiency, I mean, changes step by step. And finally, we get a 2-dimensional, I mean, correction matrix, and also feed by the spectrum. I mean, here the spectrum is just the momentum spectrum, how neutrons was selected after selection. So that gives a differential efficiency along the emission angle. So that means after 3 different comparisons from the Monte Carlo simulation weight or data weight, or from inclusive Boeing samples, that means we can get a very similar efficiency for the anti-neutron. Okay, that means we check our Monte Carlo, we check our efficiency with the Monte Carlo samples and also with our control samples, and how we can get a very, I mean, consistent result. This is our main for the this is the work that we have performed to check the number of the Monte Carlo efficiency, and also for the radiation correction, that could be determined by our Monte Carlo simulation samples with one Boeing sample and another one with the radiation correction included. So we have 2 samples, and then we just define the radiation correction factor as 1 PDF times 2 the cross section. So this is a standard way to get the radiation correction factor. That is used in many, I mean, data analysis. And also, we have to think about how our Monte Carlo efficiency is reliable or not. So that could be tested from our control sample. And here we have 10 billion GSI data. That means allow us to get a very precise efficiency correction within around 1 or 2% level. So by selecting the neutron and anti-neutron samples with this decay channel, that we can easily check how the neutron and anti-neutron response in our detector, in the time of flight detector, or in the electromagnetic calorimeter. And we just define the standard 2-dimensional correction matrix. One is along the momentum, because we have to think about the kinematic features. And for the GSI, the momentum spectrum is continuous, but in our in the form factor measurement, we just have a very narrow momentum window. So that means we have to weight our event efficiency with the momentum spectrum. So the second one, you can see here, we have so many metrics, and one is about the antineutron and about the neutron, and also about the and here is the momentum spectrum from the Monte Carlo simulation. Also, is the ratio, and the final one is here the ratio and matrix. So with this method, we can precisely calibrate our Monte Carlo efficiency with a 1 or 2% level. This is very important. And another one is the trig efficiency, since this is a pure neutral process that electron-positron annihilation to neutron and neutron. This is kind of event only triggered by the electromagnetic calorimeter. So in this case, we have to think about how many events will be triggered. So we started the trig efficiency with a similar process here. It's E plus minus annihilation proton and proton. We think about the antiproton annihilation in our detector. It's quite similar to the antineutron annihilation in our detector. So of course, they have some difference because here we have to change the track. This is quite useful for us because for most of event from this process, and we know that it will be triggered by the main drift chamber. So now we can calculate the conditional trigger efficiency in case of this kind of event were triggered by the main drift chamber. We can check how many events will be triggered by the electromagnetic calorimeter, and now we just know the energy spectrum, because here we get the energy dependent trigger efficiency correction. And here we need to know how the energy spectrum looks like. And this kind of spectrum could be extracted from the Monte Carlo simulation. Also, we have to make some correction because here the antineutron are also neutron response in our detector is different from the real case. So after the energy deposition correction, we can get more close to we can get an energy spectrum, but more close to the truth. Okay. So with these two kind of solutions, to calculations, we can now get the other two numbers, the correction number and the trig correction. Okay. Now I think that we only have the last number, the number of events. This is the last number in 5 numbers. Okay. For this number, we have to check out with 3 different kinetic features. The first one is time of flight. And for the other solutions, we use the crossing angle. So for the first case, since we know that the neutron velocity, and also in case that we know the direction of the antineutron annihilation in the EMC, that means we know the path length that from interaction point to our detector, any detector here. So that gives the time of flight difference. Okay. So with this one, we can easily to retrieve the signal features here, and also the background features. If we make the wrong particle assumption, that means the signal peak will be shifted from the 0, because here it means the signal hypothesis. It means background hypothesis. For example, this is the background from the electron-positron annihilation to the gamma, and also the other hadronic background, but with a different mass of the final state particles. Okay. And for the other ones, use the crossing angle between the antineutron and the neutron. So in this one, we just use the maximum likelihood fit to get the number of signal yield. This is very general method in experiment. Okay, now we have the 5 numbers. So it's easy to us to get the final cross sections. We have 3 independent measurements. That means we should get very close, or we should get consistent results from 3 categories. So this is very useful for our measurement, because that means if we get a very consistent result, that just proves that it's a reliability is very high. If we get very, inconsistent result, we should check what happened. It should be some bug or some potential problems in our data analysis. So now we can get 3 consistent cross sections. At most of the energies, we can say that our results are consistent in 1 standard deviation. So we can now combine the results from 3 categories and get the best measurement. Okay, now we get the most precise measurement. Of course, this is the cross section in the left plot. So, and in the red plot is the form factor, effective form factor after translating our cross section to the form factor. Okay, anyhow, this result is improved by a factor of around 30. Here I must to say that the preceding is improved by a factor of around 30, and our statistics, the number of signal events, improved by a factor of 60, almost 60, compared to the previous measurements. Okay, this is the first measurement, a very precise result. Neural data now is abundant by the BESIII experiment. And the second highlight result is we get a very precise ratios between the electron-positron annihilation to neutron and neutron, and compared to the cross-section electron-positron annihilation to proton and antiproton. So now with this ratio, we can address the puzzle that's lasting in 20 years, lasting for almost 20 years. And here we can see that the ratio is almost less than 1. Here is a reference line. The one that means the proton and neutron looks no difference for the electromagnetic probe. And clearly, they are expected to have some difference with the photon interaction. So one interesting is around the 2 GeV, from 2 GeV to 2.2 GeV. And here we can see that the ratio is almost 1/4. This is consistent with the prediction of the simple Park model. That means in that model, we only consider the difference from the charge of G Park and the charge of U Park. So here we can see that is quite interesting. It just lies in the second reference line. And for the other energies, we can see that we have some new cross-section relation, but this kind of point, it's not so easy to understand. And near the higher energies, we can see that the ratio is close to 1. However, in the most higher energy, that means in highest energy, that means the cross-section ratio, is around 1/2. So, and that means it's quite difficult to understand how the relation was. Why the relation demonstrated in such kind of shape. So this is the second conclusion. Anyhow, we can see that we clearly clarified the photon-nuclear interacting particle. There is no coupling anomaly, at least in this energy region. This is clearly true. And we also check the data points, our neural data points with the dipole. And this is a very popular or very, a very usual analysis in many publications that we just feed our data to a dipole as what we did for the space-like data. And here, this is a very, this is experimental parameter determined by the space-like data. Okay, and just define one factor here. We can check our data, and to get the difference, we just use our data subtracting from the prediction values from the dipole law, and we can the residue form factors, and we can see that the residue form factors have some, oscillation behavior, and whatever to the proton and antiproton. But the difference here, when we deal with the proton data, and we use a modified dipole, and here we can see that we have more than one form factor here, but here with only a dipole form factor, and here is actually one mono form factor times one, a dipole form factor. Okay, so then we can get the similar oscillation behavior to proton and also neutron. And the difference, they have the different phase. If we suppose that the oscillation frequency has a similar, are the same. So this is quite interesting. At least nobody predicted this behavior before me. Okay, I have to mention that this kind of analysis is inspired by another publication with the BESIII data in 2015. Yeah, this is not something. We just do the similar thing as the paper side. Okay, now let's just try to understand the form factor. So one of the quite famous or quite widely spread interpretation is the charge or magnetism distribution. And after the Fourier transformation to the form factors, we get the so-called charge density. And this is the very traditional interpretation to the space-like region data. And now let's switch to the time-like region. And we think that we can redefine a so-called generalized Fourier transformation in the four time space, And here you can see this is the generalized definition. And after that, we just connection the convolution theory and also with the form factor. And we can see that here is the form factor and the two form factor production. And then you can see that it's actually two charge distribution convolution, and then again with a Fourier transformation. So with this kind of interpretation, we can connect together to understand how form factors words really reflect the behavior in the charge density space. So this is a viewpoint with a very traditional interpretation. And another one is the quark-antiquark creation and also transition to the nuclear. This combines the so-called effective coupling, that how to treat the coupling vertex. And because for the fundamental particle, E plus minus, annihilation to muon pairs, that means here we can define the vertex with the very fundamental vertex. And here now we don't know how the hadron coupling vertex is defined. So here we just use the so-called effective coupling. And with this kind of comparison, we can calculate at a threshold how one structured particle behave like the charge. For example, for the proton, we can calculate almost, at the energy threshold, the proton behaves like, 1/2 charge in the coupling. And for the neutron, it looks like, 1/4 quark charge, here in the coupling. It's quite. This is also another, viewpoint to see how the structured particle behaves like in the coupling. And also we can understand the form factor with SU3 symmetry. And here we know that the well-defined is the octet, the bi-octet. And here we have 8 pions, and they have a very, interesting symmetry. And most of the pions are unstable. So that means we can do that, or we can measure that only in the BESIII experiment or in electron-positron annihilation experiment. So that means for proton and neutron, we can measure it with in a space-like region with the scattering experiment. But with the other 6 pions, we can't measure it with the scattering experiment. So this is unique at the BESIII experiment. However, if we look at the hadronic current here, that means we can construct a theory from the general principles to treat all 8 pions together and to construct our theory and predict all these, all data. So this is some very interesting work. And still, some theory are proposed to do that. However, I have not read some new paper to interpreting all published data together for the 8 pions. Oh, okay. This is the third viewpoint to understand the form factor. And now let me give a simple story of the nucleon picture. And with the timeline at the beginning, we treated that the nucleons as point particle. And then in the 1950s, we now observe the nucleon structure. And then we establish a well-known quark model that here the proton was interpreted as the 3 quarks, valence quarks. And in 1989, we have some new experiment reveal that the spin of the nucleon cannot be easily explained as a combination of 3 valence quarks. And then we have a modern picture of the nucleon. We know that it's just a QCD bound state, as we proposed at the beginning of this talk. And as we mentioned at the beginning of this talk, it's a valence quark plus C quark and plus gluon revolution. This is the modern picture. And in 2020, we know that the charge radius puzzle was almost solved. And in 2021, we published the result to solve the interaction or in the coupling puzzle. That clearly, I think the story still, has no ending. We now have some new calculation from the lattice QCD, and also with we know some the new equipment like electron ion collider that will be built in America, and also some of the new proposal in China. That means also electron ion collider in China is also proposed. So this kind of equipment will investigate the neutrons and also the nucleon structure continuously, and to draw a 3-dimensional picture that would answer most of the puzzles that's not solved. I think we still have many exciting results in future. And finally, let me summarize all what I talked about today. This is just a story about how the BESIII experiment carried out and solved the interacting puzzle. And before 2012, and that means the scientists from the BESIII collaboration proposed the idea and made some data taking plan. And then in 2012, from 2012 to 2015, and we performed our data taking plan and collect quite a lot of high statistics data. And after that, almost 5 years, including the publication, it's almost 5 years. Anyhow, all physics in the BESIII collaboration put their effort and contributed quite a lot in such kind of research. And today in my talk, I didn't mention their name. And this is so that's why I see this my pleasure to address this seminar, because so many people contribute quite a lot of time, spend their time and contribute their effort to carry out this research. And how in a series, formula that I would like that a measurement is just like something from a transition from idea to the fruit, and then master we have to get the amplitude, squared amplitude. And the squared amplitude operation is quite important, because after that we can make the our imaginary to the to the real. Okay, this is a statement from our measurement. And finally, this is my summary about how the BESIII experiment carried out this quite interesting research. And finally, we published our paper and get a very precise measurement. And I won't speak this or read this sentence again. So anyhow, I think we need more work to dig out the implication from our data. And this kind of thing, I think, it should be very interesting. And now I'm still working about in this field, and to try to establish or construct some models to interpret the data. Okay, that's all. Thank you. Thanks for your attention. Thank you all.
Thank you very much, Jifeng. Thank you very much. Excellent talk. We have time for questions if people have any questions.
Yeah, maybe I have some naive one here. This form factor, this oscillation feature, has this been like looked at in DIS? This is, I'm not quite sure whether the other, it looks like all this BABA and the BESS are all in E plus minus annihilation, right?
Yes.
And the form factor, in principle, one can also measure it in DIS. And there, of course, it is space-like. Has this been actually looked at in DIS, in deep inelastic scattering?
If we see the published data, including the time-like region, also the space-like region here.
Yeah.
Out the sets from the PDG book, and here for a very precise result in a space-like region, there is no such kind of oscillation here. You can see that, and of course here this is from the polarized data. This is for the polarized data. This is for the unpolarized data.
So you are saying that the oscillation feature is only in the time-like region, and you don't see that in the space-like region?
Yes, currently it is.
That's interesting. I'm wondering whether anyone has any thought on this in the audience. I have no idea how this could be.
So let me comment on that. So the oscillation could coming from the your amplitude have two terms. Stan may have different. Maybe Stan have similar comments. So you have two terms. If they have some phase difference, so that will give you oscillation. So for example, one thing I think that's when I actually did the form factor, space-like form factor calculation many years ago. I looked into this actually. So in this time lag region, when you have photon decay to baryons, so you could have helicity conserved amplitude and helicity flip amplitude. And these two amplitudes could have phase difference. And also because they have different energy dependence. So that also generates some kind of energy dependence. I mean, for PP bar, proton, anti-proton, that has been known actually. So high-end Gao actually brought my attention about like 15 years ago about this behavior. I mean, this is the first time, of course, we've seen from the neutron, anti-neutron also happens. I mean, it's back to the speakers about the neutron, anti-neutron. And if you look at the oscillation, the phase is different from PP bar. So that's another interesting feature. I actually it's quite a I don't know if there's any successful model to describe this behavior anyway.
Fong, you mean the offset?
But do you think?
Yeah.
Yeah. But why this is only happen in the time lag region, not in the space time region?
That's a very good question. I don't know. Stan, do you have any insight? Stan, are you here?
Stan?
Yeah, I'm here. Yes, it's pretty complicated. Maybe Gita Tiraman would like to comment too, but you can have also E plus E minus goes to baryon to resonances, delta,
that could be.
and then they go, and then it goes back, of course, to the neutron, anti-neutron. So it could be that you could, when you put in these secondary processes where you go to another resonance, nucleon, anti-nucleon, then you come back, that has a phase which is different than the E plus E minus neutron, anti-neutron, and that can generate these type of oscillations. But I haven't studied that in detail yet. So I mean, it's just a speculation.
So it could be that couple channel of process, right? So you
right.
have some.
That's what I'm saying. Okay. Exactly right. Yeah.
Guy, feel free to please ask or contribute.
Thank you, Jennifer, and thank you for this very interesting talk. Well, you're right. I mean, in the time lag region, you have phases that arises from the widths, from the decay widths. You don't have those in the space lag region, so it's natural to have some type of oscillation. I mean, but the deep problem is if this implies new physics or not. I mean, my feeling is not. I mean, it's just a good hadronic decay channel physics interfering the different resonances. If they are enough wide enough, then you would in principle see those oscillations. But since you have here slide 30, and you have for the proton, you have I see here a dipole, the usual dipole times a monopole with MA introduces another scale roughly, but you don't have this term for the neutron, and so they have very different analytic structures. But you see that for large Q square, then you would have 1 Q to the 4th for the neutron according to the Brodsky-Farrar counting rules, but not for the proton. So the leading count twist, you don't have a leading twist for the proton. So this parametrization is a little bit obscure for me. I don't know if Stan would like this appreciate this.
Yeah, no, I agree that I didn't understand why the power law has to be the same for the PP bar and the NN bar, but for the proton neutron.
Okay, that's essential. Good.
From
So
everything.
may I speak something here?
please do. Yes.
Yes, here currently there are some explanations about the oscillation. One is the creation could be described by one-fold exchange. And then there are some rescheduling Feynman diagrams should be counted. That means the rescheduling could be partially explained why the oscillation origins. And also another explanation is some resonance amplitude interference with the minimum amplitude. That means if we introduce some coupled state and in this energy region from 2 to 3 most GeV, that means they could explain the current data from the time-like region. But the question is, in this model, introduce the resonance, but this kind of resonance has not been tested or has not been, experimental evidence to prove that this kind of state has been just there and how their quantum properties are well verified. So that is just a model that proposed some resonance and then could be used to explain our data, but there is no, proof for this state. So currently there are two kind of explanations about how the oscillation, about the origination of the oscillation. So this is what I know now.
Just something quite interesting that I see in the data is that the oscillation in the proton and neutron seems to be quite, they are phased out. There is a phase difference in this figure. So that's quite interesting to see why this is the case. So that's a very interesting structure in the data you measured.
Guy, does that number of 125, is that evocative of anything or no?
Which I'm sorry, I missed this.
Guy, the phase shift, the value of the phase shift, the 125, is that number evocative of anything?
Oh,
no.
Let me put on my glasses. Where are you raising this one?
It's the same in slide 20, right above the two plots, the red line.
Oh, but here we have the slide 30.
Oh, sorry. I meant slide 30.
I'm sorry, okay. But what is the?
So I'm just saying he gives us the value of the phase shift. He says it's 125 degrees. And so I was just wondering if that value.
No, it doesn't sound. Oh, now I see it. Now I see it. Well, you have to translate this. I mean, from general principles, for the time-like region, you have this Ricci exchange in the T region where you have all the resonances, and so you have a product of resonances. At least that's what the holographic immediately or extended vector meson dominance model will tell you. And of course, in the space-like region, you don't have any interference. In the time-like region, of course, you have a series of resonances, each which is the K width, and you can have an interference which will give you something similar to an oscillation. But what strikes me of this data is that you see that they do not, the proton and the neutron do not coincide. So that's a very interesting structure in the data that one has to understand. Yes, so that's a very interesting point in this experiment, I believe. Yeah.
And here we can see that if we deal with the data, and this is the Barbara's data, and we have used the modified dipole law. And if we deal with neutrons data, they only are, a dipole law. So here we have the different, options to dealing with the protons data and the neutrons data. So I don't know why we, this is only, worthwhile for phenomena analysis. If we use here, we remove the first item, and we can't get a well-described, analysis. So that means then we can, obtain the oscillation and also to measure the phase shift. However, this kind of hypothesis is not, to me, it's not so solid. This is only for phenomena analysis.
Yeah, but of course, you have also isospin and you have that the proton and neutron are linear combination of isospin singlet and isospin triplet, and so it's not that simple why you can modify one of those without violating all the isospin structure. So that's why this parametrization it's difficult to accept somehow.
Stan, please contribute.
I just want to wait. One funny point is that the saccharide form, the dipole, which has got a double pole at q squared of 0.71 Jev squared, is really not analytically correct. It could be the rho and the rho prime, for example, but you never get a double pole analytically. So the saccharide form is actually not well founded, but it can be, for example, a pole at the rho and then a pole at the rho prime, and that can give you the something close to the dipole, but it's never really the same pole at the same place. And there's no model that I believe that analytically gives you a double pole. Somebody can correct me maybe on that, but I think there's a whole story that's interesting about that it's never, that form is convenient, but it's not really analytically plausible.
Stan, you're totally right, and not only analytically, also physically, because you are exchanging all the resonances along the rigid trajectory. So it's not physically well founded to have the dipole. Indeed, as you mentioned, you should have the whole chain of radial excitations. Indeed, that's a good point.
Very good, thank you.
Maybe one more point, I guess, is that nowadays also we think about the three quarks as a quark diquark model too, where the U and the D clusters is spin zero diquark, and then the U quark and the proton is then a bound state with the U quark with the UD diquark. Jennifer actually works a lot with that model too, and that's very successful for phenomenology, for understanding Regge trajectories and things like that. So that's another ingredient that has to be thought about. It's really not a three quark system. It's really more or less a quark diquark system, at least to leading twist.
But Stan, this will change power behavior, right?
Oh no, because of course you're right, but the diquark itself is not elementary. It's a composite. It's like the pion.
I understand. So that would be suitable for no Q score, maybe calculation.
That's what, it doesn't modify the leading twist behavior, but it's still a much more physical model that it's actually, and that's how you get, in fact, the Regge trajectories for the proton matches the Regge trajectory for the pion, because they're both, to first approximations, quark antiquark 3-3 bar approximations. And that's how you get, in fact, these supersymmetric relationships between the meson trajectory and the baryon trajectory.
So Stan and Guy, another comment. So I just look at the paper in 2015. When they fit to the proton antiproton data, the MA factor for the additional dipole behavior for the proton, MA is very large. Let me see.
Let's see. Thank you.
So MA score is equal to 15 GeV score. So in this kinematics, I think that doesn't really give you much of the power behavior. I think this
Thank you for
penetration
clarifying
was
that.
actually in the paper was motivated by your calculation many years ago with Lepage. When you have large Q-square power counting, you not only have the 1 Q-square power counting, but also have alpha S. So this alpha S would give additional decreasing function as a function of the Q-score. So I guess I didn't read the paper carefully, but I think that's one of the motivation when they added this additional separation factor. I mean, of course, curiously, why BESIII, when they fit the neutron data, why they're not using the same phone?
That's
I mean, with the same MA, actually, this doesn't change much, actually. I mean, you just maybe put another parameter there. Yeah.
Thank you for clarifying that. That was confusing.
Yeah.
Okay, so if we only from the viewpoint of phenomena analysis, that means to get the best formula to fit our data, the depot is the most best choice. This is concluding from the chi-square fit. If we use some other kind of formula, that means it's more or less it's not as so good as the double law.
So, Jifeng, let me ask you a question. Is there any going to be some improvement for future data, or so this will be state? So this precision will be there for forever. So you do you have a future plan to do this measurement again?
Okay, so as a spokesperson from BESIII collaboration side, in the future we will make some machine time to invest some machine time to collect some data around here, and because now you can see that we have the data. And also in the white book of the BESIII published the white book, and below the 2 GeV, and also from the energy threshold here, and 2 mGeV, we have some a plan to take data around this energy region.
Mm-hmm. That's cool.
Jifeng, but didn't you say it wasn't there an energy cut in an earlier slide that said below 2 GeV is a problem?
No, actually it's not a real problem, just because the collider, I mean the collider, the scientists from the collider, that means they think that if they put a lot of effort to collect data here, they must do tuning the collider and put a lot of effort. They don't want to do that at that time.
Okay. Very nice. Well, if there are no more questions, Jifeng, I want to thank you again from all of us for a wonderful talk. And I hope everyone has a happy holiday.
Oh, thank you. And I'm very glad to accept your invitation. Actually, before, I mean, before the Paul forward the email to me, I mean, I don't know, I have this kind of chance to talk about this work. And of course, I mean, I wish you have the same very exciting holiday. I think we have one day difference or half the difference.
Yes.
Okay, tomorrow. Okay.
Okay, thank you.
Thank you.
Thank
Bye-bye.
you. Very nice talk. Bye.
Happy holidays, everybody.